Okay, YouTube, my last two videos we discussed direct and inverse variation. What we're going to do is we're going to look at joint variation in this video, and really what I want to do is I want to kind of point out the fact that it is just an extension of direct variation. So we say that direct variation are two variable types. We say like y and x. If they vary directly, then we'd say that they're on opposite sides of the equation, typically listed that way. And we say they're on the same level. That is, these are both in the numerator. They could also both be in the denominator, but we say where k is our constant of variation. Whenever we discuss, joint variation, really what this is a direct variation in which maybe y doesn't just vary directly with x, but y varies directly with x and maybe b. And we could say that there's more than one variable type over here with a single constant of variation, but that are all on the same level with this, and we could say that that's very true. So for instance here we would say that the area of a shape varies directly with its length and its width. There would be some constant in the way it might vary, definitely. This could be some type of a model we use here, but this would be joint variation where the area varies directly, but with more than one variable type other than itself. So we'd say A, or the area, varies jointly with the length and the width. And so that's all this means. So we say, more generally speaking, if we were to say z is varying jointly with x and y, we would say that z, x, and y are on different sides of the equation and all in the numerator more typically, and there is some constant of variation still. So I'm going to run through a couple of examples here. One, kind of a word problem. The other one more just kind of general, abstract. So let's look at example 5 here. It says z varies jointly with x and y. The very first thing we want to do when we hear this right here is write down our model. So we say z varies jointly with x and y. Well, that means that z and x and y are on different sides of this equation, and they're all on the same level, and we have some constant of variation here. So what we're told is when z is equal to 6, x is equal to 3, and y is equal to 8 respectively. So in the past here we kind of wrote out a table, and this isn't stopping us from doing so. It would just say that we have a z with an x and a y. And so we would say z is 6, but only when x is equal to 3 and y is equal to 8. So what I'm going to do is I want to go plug these values in to go solve for, well then what is this constant of variation, so that we can write a model that more generally describes what this is doing in this situation all the time. So we say z is equal to k times x times y. We say z is 6, but only if x is equal to 3 and y is equal to 8. So in other words, 6 equals 24k, and k is equal to 6/24, or in other words, a fourth. So our model, this thing that I'm going to write right here, this model should say, well then z is equal to our constant of variation, which is a fourth, times x and y. This is our model. And so what we want to do now is this: we want to find z when x is equal to -4 and y is equal to 7. So we would say, well, and I'll put in a -4 for x and I'll put in a 7 for this. And I'll say, well then what is this? And so using our model here, we say z equals 1/4 x times y, where we have x is -4 and y is 7. In other words, I suppose we could say that this 1/4 and the -4 cross cancel. This would become a -1, and -1 times 7 is a -7. But we would say then I could determine that this value here must be a -7. Okay. So now looking at word problems, which are really the crux of why we do these. When we practice with variable letters, then that's just practice. But when we look at something like example 6, we're going to start by writing our model first using letters we choose, and then plugging in knowns to find our constant of variation, and then working backwards to kind of predict other values. So it says the volume of a pyramid varies jointly as its height and the area of its base. So let's go ahead and point a few things out here. We say the volume varies jointly, that's kind of a key word there, as its height and the area of the base. So we could say that the volume varies jointly. That means that they're all on the same level, but with the height, I'm going to use a capital H here, and the area. Actually, I'm going to use a lowercase h. We say the height and the area, and we say k is our constant of variation. So here's our joint variation. Everybody's on the same level but opposite sides. So what we're told here, I suppose we could say, is that there's a relationship between the volume and the height and the area. Okay, we could say that the volume depends upon these two things. And so they also tell us this: if a pyramid has a height of 12 feet, so I'm going to write this in here, 12 feet, and a base with an area of 23 square feet, so we know the number of square feet in the base, and it also has a volume of 92 cubic feet at that point, then we kind of have an insight into what this k value would be. So we're going to go back and we're going to solve for k. We say volume equals our constant of variation times the height and the area value. So we'd say when the height is equal to 12 and the area is 23, and we get a volume of 92, and this is all in feet. So we have a height of feet, area of feet squared, and of course a volume of cubic feet. So I'm going to go ahead and get my calculator out here, and I'm going to say the first thing I would do is take 12 times 23. So 12 times 23, I get 276. So we would say that 92 is equal to 276k, and it follows then that k is equal to 92 over 276. Now I think it's important to write that as a fraction first as an exact value. But let's go ahead and take 92 divided by 276, see if we can dig out a reasonable decimal here. So it's a third. So I'm actually going to reduce that to a third, and I would say, well, then my model, I'm going to write this over here, is just going back and putting this in for k. This is our constant of variation here. We would say, well, then the volume here is equal to our k, which is a third, times the height in the area. So now what we want to do is this. It says find the volume. So we're going to be looking for a volume here. We don't know the volume, but I will say, but when the height is 17 feet and the area is 27 square feet. So we say 17 feet, 27 square feet. Well, then we'd say the volume is 1/3 times our height, which is 17, times our area, which is 27 square feet. And so we would say 17 times 27. Let's do this. We say 17 times 27. And if we take that times a third, that's really going to divide this by 3, but we get about a volume of 0.17647. 0.17647. Okay, and that's not very big. I just want to check on this again. That's really small. We say 17 times 27. This is much more reasonable. Sorry, everybody, I must have left some value in here. We say 153. So we would say 153, and since this is a volume, notice we were measuring volume in cubic feet. So we're going to want to label this every time we do a word problem. We say, well, then the volume must be equal to 153 cubic feet if the height's 17 feet and the area of the base is 27 square feet. So that's how you deal with joint variation and how it's basically an extension of direct variation. Cheers.